Sweet. All right. In this video, what I want to do is we're going to put together two things we already know and kind of hopefully tie things together and hope it makes sense. And this is idea of polar molecules, and we'll get into that in a second. So this is going to require us to know two things: uh, polar and nonpolar bonds, which we'll talk about again, and molecular geometry, which we've been going over that Vesper theory stuff, tetrahedral, square planar, and all that. Um, I love this gift that I found up here because it's showing us, right, if this is a charged plastic rod, right, and it's showing us that if you have a charged plastic rod and you move it in front of a stream of liquid, that the liquid could be attracted or repelled from the rod or not, right? In the case of hexane, it's not. There's no effect of the charged rod on the hexane, but the water and the isopropanol both do that. And the reason the charged rod can tweak the water and the isopropanol is because those are polar molecules, um, while the hexane is a non-polar molecule. And we'll get into a little bit of what that means as we do stuff. This, again, is one of those more important things that we're going to have to carry with us through all of our Gen Chem and organic classes and beyond if you're doing that. Okay. So hopefully we can get our hands on this and talk about some stuff. All right. So let's talk about what we're thinking about here. Let's kind of refresh ourselves on nonpolar and polar bonds. Remembering we talked about this, we said bonding was a continuum, right? And at one end of the spectrum, we have nonpolar. In the case of a nonpolar, oh, crow, I'd never seen that before. I'm sorry. What the heck? There we go. I don't know what happened. Um, on the one end of it, we have nonpolar. Nonpolar stuff is usually when there's two things that are the same, right? Here we're using hydrogen as our example, but two atoms the same are nonpolar. Carbon and hydrogen together are nonpolar. Things on the other end of the spectrum here are ionic. These are things that have a metal and a non-metal, right? Metal with something, and these have definite positive and negative charges. Okay. When we're thinking about polar molecules, we're not going to focus on ionic quite at all because we're thinking about molecules. So all these are covalent bonds. Okay. In the middle, we have this polar case. And remember, in a polar bond, that's anything that's not non-polar. So these are different atoms in a covalent bond. Okay. Remembering that we can determine which way, right? We're going to use our HF example here too. We can determine the polarity of the bond, right? One end of this is going to be kind of negative and one end of this is going to be kind of positive. And we can figure that out based off of the electronegativity. Remembering that fluorine is the most electronegative, so this is our delta minus end. The hydrogen end then becomes delta plus. This sets up our dipole moment vector that looks like this. So remember, it always starts on the positive and points towards the negative. Okay. Now, the neat thing is that the polar and nonpolar bonds, really the polar bonds tweak us a little bit and let us have uh, polar or nonpolar molecules. So we're thinking now we're going to take our polar bonds and put them into 3 dimensions on top of the geometry and look at it that way. Okay. If you've had any sort of physics or anything like this is going to help a little bit because we're going to looking at adding vectors together. Okay. Um, all right. So here's an example. If we have, this is CO2, carbon dioxide. Okay. Um, and these are not the same atoms and they're not carbon and hydrogen bound to each other. So these are polar bonds. And in each case, the oxygen is more electronegative. So we're going to have a dipole that pulls that way and a dipole that pulls that way. Remember, we talked about tug of war, right? The atoms are pulling at each other. The same thing is true with the bonds, right? This CO bond is pulling to the right. This CO bond is pulling to the left. And because they're the same atoms hooked to it, they're pulling equally strong. And so really everything cancels out, right? If you think at it from a vector standpoint, one of them is pointing exactly this way to the right, one is pointing to the left, and they cancel each other out. So our overall total is going to be 0 dipole moment. So this thing is non-polar because the vectors have canceled out. Okay. If we look at water now, water, and oftentimes when we draw water, we'll draw it, and this is a perfectly reasonable Lewis structure, but it's not what water looks like, remember, right? We'll often draw water like this. which is totally fine for a Lewis structure, but it doesn't really help us in terms of geometry. So we want to remember that that has 4 electron groups, 2 of them are lone pairs, and that makes this dude bent. Okay, because it's bent, right, and because the oxygen is more electronegative, we've set up 2 polar bonds, and each of them points from the hydrogen to the oxygen. Okay, so what happens now is we can put this on the coordinate system and look at it. They're pointing away from each other like so. Okay, but they're both pointing slightly up. And when they're, so if you look at it, the x part of the vector, right? So this part, right, cancels out. This part they've added together and doesn't cancel out. So this piece over here and this piece over here cancel each other out. That's what they're saying, the sum of x equals 0. Okay. When you're looking at the other piece of this, there's no down, right? Nothing in here is pointing down to cancel out all the stuff that's pointing up. So the y, the pointing up part, is not equal to 0. So overall, this thing has leftover dipole moment, and this thing is polar. Okay. Um, we can look at this guy. This is BF3, boron in the middle, and 3 fluorines. And if you remember, fluorine being the most electronegative element, they've already drawn our dipole moment vectors on here for us, but we can kind of see it. Remember, boron in the center, 3 fluorines. So all of these are pointing from the middle to the outside. And all 3 of those are fluorine, so they're pulling equally, and they're all pulling opposite. So I look at this and it looks to me like CO2 because they're all pulling equally and they're all pulling opposite of each other. From a vector standpoint, we can look at it this way, right? There's the vector that points straight up, and then there's 2 that are angled kind of down. Okay, and just like we saw with water, the horizontal pieces of the down, this purple and black isn't working for me, I'm sorry. The horizontal pieces on the down ones cancel each other out. Okay, but now there's a down part in the vertical because those are pointed down, and the down vertical and the down, I keep saying down vertical, the down vertical and the up vertical cancel each other out. So here everything is 0 again, and this is non-polar. Okay, so really what we're seeing here is you can have polar bonds and be a non-polar molecule as long as all of your vectors cancel out. Okay, if you have any left over, right, here's our leftover dipole moment, anything left over is going to mean that molecule is polar. Okay, let's look at this guy. This is the same, not really the same, but it's the same idea, right? This is CCl4, carbon tetrachloride. Okay, and again, all 4 bonds are equal, right? This is 4 bonds now, so this is tetrahedral, so it looks a little bit wackier, but it's the same idea, right? They're all pulling equal and opposite of each other. And if you put them on the coordinate system, right, we have one bond that lines up along the y-axis going this way, right? All of the horizontals of the guys that the other 3 are canceling each other out because they're going around and they're all pulling equal and opposite. The vertical part of the down is canceled out by the vertical part of the up, and this whole thing is nonpolar. Okay. If, however, we replace one of those with a hydrogen, okay, it looks like this. And now we're not pulling equal and opposite in all directions, and now it is no longer nonpolar. This is polar. This is chloroform, CHCl3. This guy was nonpolar. Oh, I'm sorry. Okay. All right. We can look at the same thing down here. These 2 compounds are isomers of each other, right? The dichloroethylene. Okay, we're not going to worry about naming stuff, but they are opposites. They are isomers of each other, meaning they have the same formula, but their shapes are different. Okay, their molecules are different. Okay, the one on the left here has the 2 chlorines opposite of each other, and they're pulling equal and opposite. So this is non-polar. Okay, and this one, they're pulling equally, but they're not exactly opposite. They're both pulling down. So there's a net down through here. Because there's a net down through here, This is polar. Okay. This is a nice little summary chart. It's not perfect because there's no perfect way to do this very generally. But typically, as long as all the atoms around your central atom are the same, these rules hold true. Okay. And a good rule of thumb is if your central atom has a lone pair, it's most likely going to be a polar molecule, but it might not necessarily be a polar molecule. Um, and if you have different atoms in there, they're probably going to not cancel each other out completely. Okay. Hopefully that made a little bit of sense. We can always discuss stuff and practice, 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 right? Remembering the nonpolar versus polar bonds and how your vectors are canceling out. Okay. I'll catch you next time. Let me know if you need anything.